The kinetic theory of gases describes a gas as a large number of submicroscopic particles, atoms or molecules, all of which are in constant, rapid, random motion. The randomness arises from the particles' many collisions with each other and with the walls of the container. Kinetic theory of gases explains the macroscopic properties of gases, such as pressure, temperature, viscosity, thermal conductivity, and volume, by considering their molecular composition and motion. The theory posits that gas pressure results from particles' collisions with the walls of a container at different velocities. Kinetic molecular theory defines temperature in its own way, in contrast with the thermodynamic definition. Under an optical microscope, the molecules making up a liquid are too small to be visible. However, the jittery motion of pollen grains or dust particles in liquid are visible. Known as Brownian motion, the motion of the pollen or dust results from their collisions with the liquid's molecules. History. In approximately 50 BCE, the Roman philosopher Lucretius proposed that apparently static macroscopic bodies were composed on a small scale of rapidly moving atoms all bouncing off each other. This Epicurean atomistic point of view was rarely considered in the subsequent centuries, when Aristotelian ideas were dominant. In 1738 Daniel Bernoulli published Hydrodynamica, which laid the basis for the kinetic theory of gases. In this work, Bernoulli posited the argument, still used to this day, that gases consist of great numbers of molecules moving in all directions, that their impact on a surface causes the gas pressure that we feel, and that what we experience as heat is simply the kinetic energy of their motion. The theory was not immediately accepted, in part because conservation of energy had not yet been established, and it was not obvious to physicists how the collisions between molecules could be perfectly elastic. Other pioneers of the kinetic theory, which were neglected by their contemporaries, were Mikhail Lomonosov (1747), Georges Louis Lesage (ca. 1780), published 1818, John Herapath (1816), and John James Waterston 1843, which connected their research with the development of mechanical explanations of gravitation. In 1856 Auguste Kronig, probably after reading a paper of Waterston, created a simple gas kinetic model, which only considered the translational motion of the particles. In 1857 Rudolf Clausius, according to his own words independently of Kronig, developed a similar, but much more sophisticated version of the theory which included translational and, contrary to Kronig, also rotational and vibrational molecular motions. In this same work he introduced the concept of mean free path of a particle. In 1859, after reading a paper on the diffusion of molecules by Rudolf Clausius, Scottish physicist James Clerk Maxwell formulated the Maxwell distribution of molecular velocities, which gave the proportion of molecules having a certain velocity in a specific range. This was the first ever statistical law in physics. Maxwell also gave the first mechanical argument that molecular collisions entail an equalization of temperatures and hence a tendency towards equilibrium. In his 1873 13-page article Molecules, Maxwell states, "We are told that an atom is a material point, invested and surrounded by potential forces, and that when flying molecules strike against a solid body in constant succession it causes what is called pressure of air and other gases." In 1871, Ludwig Boltzmann generalized Maxwell's achievement and formulated the Maxwell–Boltzmann distribution. Also, the logarithmic connection between entropy and probability was first stated by him. In the beginning of the 20th century, however, atoms were considered by many physicists to be purely hypothetical constructs, rather than real objects. An important turning point was Albert Einstein's 1905 and Marian Smoluchowski's 1906 papers on Brownian motion, which succeeded in making certain accurate quantitative predictions based on the kinetic theory. Assumptions. The theory for ideal gases makes the following assumptions. The gas consists of very small particles known as molecules. This smallness of their size is such that the total volume of the individual gas molecules added up is negligible compared to the volume of the smallest open ball containing all the molecules. This is equivalent to stating that the average distance separating the gas particles is large compared to their size. These particles have the same mass. The number of molecules is so large that statistical treatment can be applied. The rapidly moving particles constantly collide among themselves and with the walls of the container. All these collisions are perfectly elastic. This means the molecules are considered to be perfectly spherical in shape and elastic in nature. Except during collisions, the interactions among molecules are negligible. That is, they exert no forces on one another. This implies 1. Relativistic effects are negligible. 2. Quantum mechanical effects are negligible. This means that the inter-particle distance is much larger than the thermal de Broglie wavelength and the molecules are treated as classical objects. 3. Because of the above two, their dynamics can be treated classically. This means that the equations of motion of the molecules are time reversible. The average kinetic energy of the gas particles depends only on the absolute temperature of the system. The kinetic theory has its own definition of temperature, not identical with the thermodynamic definition. The elapsed time of a collision between a molecule and the container's wall is negligible when compared to the time between successive collisions. There are negligible gravitational force on molecules. More modern developments relax these assumptions and are based on the Boltzmann equation. These can accurately describe the properties of dense gases, because they include the volume of the molecules. The necessary assumptions are the absence of quantum effects, molecular chaos and small gradients in bulk properties. Expansions to higher orders in the density are known as virial expansions. An important book on kinetic theory is that by Chapman and Cowling. An important approach to the subject is called Chapman-Enskog theory. There have been many modern developments and there is an alternative approach developed by Grad based on moment expansions. In the other limit, for extremely rarefied gases, the gradients in bulk properties are not small compared to the mean free paths. This is known as the Knudsen regime and expansions can be performed in the Knudsen number. Equilibrium properties. Pressure and kinetic energy. In kinetic model of gases, the pressure is equal to the force exerted by the atoms hitting and rebounding from a unit area of the gas container surface. Consider a gas of n molecules, each of mass m, enclosed in a cube of volume 5 equals L3. When a gas molecule collides with the wall of the container perpendicular to the x-axis and bounces off in the opposite direction with the same speed, an elastic collision, the change in momentum is given by delta p equals p I x minus p f x equals p I x minus p I x equals 2 p I x equals 2 m v x. display style delta p equals p underscore I x p underscore f x equals p underscore I x p underscore I x equals 2 p underscore I x equals 2 mv underscore x, where p is the momentum, I and f indicate initial and final momentum before and after collision, x indicates that only the x direction is being considered, and v is the speed of the particle, which is the same before and after the collision. The particle impacts one specific side wall once every delta t equals 2 L v x display style delta t equals frac 2 L v underscore x, where L is the distance between opposite walls. The force due to this particle is F equals delta p delta t equals m v x 2 L display style F equals frac delta p delta t equals frac mv underscore x caret 2 L. The total force on the wall is F equals n m v x 2 L display style F equals frac nanometer overline v underscore x caret 2 L, where the bar denotes an average over the n particles. Since the motion of the particles is random and there is no bias applied in any direction, the average squared speed in each direction is identical. V x 2 equals v y 2 equals v z 2. Display style overline v underscore x caret 2 equals overline v underscore y caret 2 equals overline v underscore z caret 2. By Pythagorean theorem in 3 dimensions, the total squared speed v is given by v 2 equals v x 2 plus v y 2 plus v z 2. Display style overline v caret 2 equals overline v underscore x caret 2 plus overline v underscore y caret 2 plus overline v underscore z caret 2. V 2 equals 3 v x 2. Display style overline v caret 2 equals 3 overline v underscore x caret 2. Therefore, v x 2 equals v 2 3. Display style overline v underscore x caret 2 equals frac overline v caret 2 3. And the force can be written as F equals n m v 2 3 L. Display style F equals frac nanometer overline v caret 2 3 L. This force is exerted on an area L2. Therefore, the pressure of the gas is P equals F L 2 equals N M V 2 3 V display style p equals frac f l caret 2 equals frac nanometer overline v caret 2 3 volts, where V equals L3 is the volume of the box. In terms of the kinetic energy of the gas K, P V equals 2 3 times K. Display style PV equals frac 2 3 times K. This is a first non-trivial result of the kinetic theory because it relates pressure, a macroscopic property, to the translational kinetic energy of the molecules N 1 2 m v 2 display style N frac 1 2 m overline v caret 2, which is a microscopic property. Topic: Temperature and kinetic energy. Rewriting the above result for the pressure as P V equals N m v 2 3 display style PV equals nanometer overline v caret 2 over 3. We may combine it with the ideal gas law, where K B display style K underscore B is the Boltzmann constant and T display style T the absolute temperature defined by the ideal gas law. To obtain K B T equals m v 2 3 display style K underscore B T equals m overline v caret 2 over 3, which leads to simplified expression of the average kinetic energy per molecule 1 2 m v 2 equals 3 2 K B T display style frac 1 2 m overline v caret 2 equals frac 3 2 K underscore B T. The kinetic energy of the system is n times that of a molecule, namely K equals 1 2 n m v 2 display style K equals frac 1 2 nanometer overline v caret 2. Then the temperature T display style T takes the form which becomes EQ 3 is one important result of the kinetic theory. The average molecular kinetic energy is proportional to the ideal gas law's absolute temperature. From EQ 1 and EQ 3, we have thus the product of pressure and volume per mole is proportional to the average translational molecular kinetic energy. EQ 1 and EQ 4 are called the classical results, which could also be derived from statistical mechanics. For more details, see, since there are 3 n display style 3n degrees of freedom in a monatomic gas system with n display style n particles. The kinetic energy per degree of freedom per molecule is in the kinetic energy per degree of freedom the constant of proportionality of temperature is 1/2 times Boltzmann constant, or R, 2 per moles. In addition to this, the temperature will decrease when the pressure drops to a certain point. This result is related to the equipartition theorem. As noted in the article on heat capacity, diatomic gases should have 7 degrees of freedom, but the lighter diatomic gases act as if they have only 5. Monatomic gases have 3 degrees of freedom. Thus the kinetic energy per Kelvin monatomic ideal gas is 3 R2 equals 3 R2 per mole, 12.47 J per molecule, 20.7 Yj equals 129 μeV. At standard temperature 273.15 K, we get per mole 3406 J per molecule 5.65 Zj equals 35.2 MeV. Topic: Collisions with container. One can calculate the number of atomic or molecular collisions with a wall of a container per unit area per unit time. Assuming an ideal gas, a derivation results in an equation for total number of collisions per unit time per area. N equals 1 4 N V V AVG equals N 4 8 K B T pi M. Display style n caret asterisk equals frac 1 4 frac n v v underscore text avg equals frac n 4 sqrt frac 8 k underscore b t pi m. This quantity is also known as the impingement rate in vacuum physics. Topic: Speed of molecules. From the kinetic energy formula it can be shown that V P equals 2 K B T M. Display style V underscore text P equals sqrt 2 cdot frac K underscore B T M. V equals 2 pi V P equals 8 pi K B T M. Display style bar V equals frac 2 sqrt pi V underscore P equals sqrt frac 8 pi cdot frac K underscore B T M. V RMS equals 3 2 V P equals 3 K B T M. Display style V underscore text RMS equals sqrt frac 3 2 V underscore P equals sqrt 3 cdot frac K underscore B T M, where V is in meter per second, T is in kelvins, and M is the mass of one molecule of gas. The most probable or mode speed V P display style V underscore text P is 81.6% of the RMS speed V RMS display style V underscore text RMS, and the mean arithmetic mean or average speed V display style bar V is 92.1% of the RMS speed, isotropic distribution of speeds. C average, root mean square speed, arithmetic mean, mean mode statistics. Topic: Transport properties. The kinetic theory of gases deals not only with gases in thermodynamic equilibrium, but also very importantly with gases not in thermodynamic equilibrium. This means considering what are known as transport properties, such as viscosity and thermal conductivity. Topic: Viscosity and kinetic momentum. In books on elementary kinetic theory, one can find results for dilute gas modeling that has widespread use. Derivation of the kinetic model for shear viscosity usually starts by considering a couette flow where two parallel plates are separated by a gas layer. The upper plate is moving at a constant velocity to the right due to a force F. The lower plate is stationary, and an equal and opposite force must therefore be acting on it to keep it at rest. The molecules in the gas layer have a forward velocity component u, u, which increase uniformly with distance y, y, above the lower plate. The non-equilibrium flow is superimposed on a Maxwell-Boltzmann equilibrium distribution of molecular motions. Let sigma sigma be the collision cross-section of one molecule colliding with another. The number density c c is defined as the number of molecules per extensive volume. C equals n v. Display style C equals n v. The collision cross-section per volume or collision cross-section density is C sigma. Display style C sigma, and it is related to the mean free path L display style L by L equals 1 2 C sigma display style quad L equals frac 1 sqrt 2 C sigma. Notice that the unit of the collision cross section per volume C sigma display style C sigma is reciprocal of length. The mean free path is the average distance traveled by a molecule, or a number of molecules per volume, before they make their first collision. Let u 0 display style u underscore 0 be the forward velocity of the gas at an imaginary horizontal surface inside the gas layer. On the average, a molecule that crosses the surface makes its last collision before crossing at a distance equal to 2/3 of the mean free path, i.e. 2 L 3 display style 2 L 3 away from the surface. At this distance above and below the surface, the forward momentum of the molecule is respectively p x plus or minus equals m u 0 plus or minus 2 3 L d u d y display style quad p underscore x caret pm equals m left u underscore 0 pm frac 2 3 L do over dy right, where m is the molecular mass. The molecular flux phi phi includes all molecules arriving at one side of an element of the surface within the gas layer. The incoming molecules are coming from all directions at the one side of the surface and with all speeds. This molecular flux, i.e., the number flux, is related to the average molecular speed v bar v by phi equals 1,4 v c display style quad phi equals frac 1,4 bar v c. Notice that the forward velocity gradient d u d y display style do dy can be considered to be constant over a distance of mean free path. Next we multiply by the total flux to get the change of momentum per unit time and per unit area, that is carried by the molecules crossing from either above or below the surface area. This gives the equation phi p x plus or minus equals 1,4 v c m u 0 plus or minus 2 3 l d u d y display style quad phi p underscore x caret pm equals frac 1,4 bar v c c dot m left u underscore 0 pm frac 2 3 l do over dy right. The net rate of momentum per unit area that is transported across the imaginary surface is thus tau equals phi p x plus minus phi p x minus equals 1 3 v c m l d u d y display style quad tau equals phi p underscore x caret plus phi p underscore x caret equals frac 1 3 bar v cm c dot l do over dy. The defining equation for the shear viscosity eta display style eta of the gas is f a equals eta d u d y display style quad frac f a equals eta do over dy. Combining the above kinetic equation with defining equation for shear viscosity by tau equals f a display style tau equals f a gives the equation for shear viscosity, which is usually denoted eta 0 display style eta underscore 0 when it is a dilute gas. Eta 0 equals 1 3 v c m l display style quad eta underscore 0 equals frac 1 3 bar v cml. Combining this equity on with the equation for mean free path gives eta 0 equals 1 3 2 m v sigma display style quad eta underscore 0 equals frac 1 3 sqrt 2 frac m cdot bar v sigma. From statistical thermodynamics for gases we have equations relating average molecular speed to most likely speed and further to temperature. These statistical results gives the average equilibrium molecular speed as v equals 2 pi v p equals 2 pi k b t m. Display style quad bar v equals frac 2 sqrt pi v underscore p equals 2 sqrt frac 2 pi cdot frac k underscore b t m underscore, where v p display style v underscore p is the most probable speed, k b display style k underscore b is the Boltzmann constant. We note that k b n a equals r and m equals m n a. Display style quad k underscore b cdot n underscore a equals r quad text and quad m equals m cdot n underscore a, and insert the velocity in the viscosity equation above. This gives the well-known equation for shear viscosity for dilute gases. Eta 0 equals 2 3 pi m k b t sigma equals 2 3 pi m r t sigma n a. Display style quad eta underscore 0 equals frac 2 3 sqrt pi cdot frac sqrt mk underscore b t sigma equals frac 2 3 sqrt pi cdot frac sqrt mrt sigma cdot n underscore a and m display style m is the molar mass. The equation above presupposes that the gas density is low, i.e. the pressure is low. This implies that the kinetic translational energy dominates over rotational and vibrational molecule energies. The viscosity equation further presupposes that there is only one type of gas molecules, and that the gas molecules are perfect elastic and hard core particles of spherical shape. This assumption of elastic, hard-core spherical molecules, like billiard balls, implies that the collision cross-section of one molecule can be estimated by sigma equals pi 2 r 2 equals pi d 2. Display style quad sigma equals pi left 2r right caret 2 equals pi d caret 2. The radius r display style r is called collision cross section radius or kinetic radius, and the diameter d display style d is called collision cross-section diameter or kinetic diameter of a molecule in a monomolecular gas. There are no simple general relation between the collision cross-section and the hard core size of the fairly spherical molecule. The relation depends on shape of the potential energy of the molecule. For a real spherical molecule, i.e. a noble gas atom or a reasonably spherical molecule, the interaction potential is more like the Lennard-Jones potential or Morse potential, which have a negative part that attracts the other molecule from distances longer than the hard core radius. The radius for zero Lennard-Jones potential is then appropriate to use as estimate for the kinetic radius. Local nomenclature list. See also: Bogolyubov-Born-Green-Kirkwood-Evon hierarchy of equations, Boltzmann equation, collision theory, critical temperature, gas laws, heat, interatomic potential, magnetohydrodynamics, Maxwell-Boltzmann distribution, Mixmaster dynamics, thermodynamics, Vlasov equation. Notes